Okay, everyone, it's 7:15. I would like to welcome everyone here to the Chicago Chromatography Discussion Group. After a 4-year hiatus, we're proud to be back in action. And we've been discussing with excitement the continuation of the history of this storied organization, one of the oldest organizations for this purpose in the country. So again, I'd like to welcome everyone here. I hope you enjoy our program tonight. Before we begin tonight, I want to take an opportunity to thank our sponsor for this event. AB SciEx is very important for us, and without our sponsors, events like this would not be possible. I'd like to recognize Scott Harder. He is the Senior Mass Spectrometry Sales Representative from AB SciEx. And so please, everyone, make sure that you meet Scott before we leave tonight. And there's Scott. You can't miss him. He's the big, really tall guy. You can't miss him. So Scott, we really appreciate your assistance with the CCDG in this event. So now for tonight's speaker. We have a local scientist who grew up just down the road in Villa Park. After stints with the Northwestern University Medical School and Children's Memorial in Chicago, he founded United States Drug Testing Laboratories. Back then it was located at the Technology Center at UIC, and after they outgrew that facility, it moved into Des Plaines where we currently are, 23 years. He served as a co-principal investigator and a co-investigator on numerous National Institutes of Health funded grants. And he's been a leader in newborn toxicology with his innovative and creative approach to solving some very difficult toxicological questions. So please welcome the founder, the president, the scientific director of United States Drug Testing Laboratories, Douglas Lewis.
Wow. Does that sound like you? This is amazing. For the first official venue for the reincarnated Chicago Chromatography Discussion Group, a group that helped teach me gas chromatography when I was a graduate student, a very long time ago, before I ventured into toxicology, when I was a budding neuropharmacologist, pharmacokineticist, in a very, seems like ages ago. But what I'm going to do today is tell you a little bit about a journey that I've been on and an adventure. And it's a lot of science, but also a lot of history as I recall it. And it's from the point of view of the history as I saw it happening. So, just how in the world did I get involved in this adventure of direct alcohol biomarker discovery? It started when I got off the elevator on the top floor at Children's Memorial Hospital in the fall of 1983. I was in tow with Dr. Ira Chasnoff, who had collared me earlier in the week and gave me a test tube of urine. A test tube of urine. He gave me about 3 drops of pee and asked me to figure out what was in this baby's urine. Baby was presenting differently from the T's and Blues babies that they were used to seeing. T's and Blues was the drug of abuse that was the most common thing seen on the streets in those days. T's and Blues, for those of you who are under the age of 60, was an opioid combo. The opioid was pentazocine, not very commonly used anymore these days. Mixed with the blues part was an over-the-counter antihistamine called triple-enamine. And you put the mixture together and shot it up, and folks said it was as good as heroin. So we were seeing a lot of T's and Blues babies. I had nothing to do with them at that time. I had joined the faculty at Northwestern in November of 1992 in the pathology department, and my service position was at Children's Memorial. I was there to set up a functioning toxicology laboratory. So there I was, going into this NICU, and my activities at that time were involved with, I was the team toxicologist for the United States Weightlifting Federation. I was involved with jocks, high-performance athletes. I had just gotten my first GCMS system because the team doc for the weightlifters, who was an orthopedic surgeon that I happened to have had as a classmate, and he lived down the hallway from me as undergraduates. We were chem majors together. He dated my sister, so we were kind of good friends, even though they'd broken up. And I was involved with kids at Children's, looking at therapeutic drug monitoring a little bit. I wasn't really doing newborns, I was doing kids. So I really didn't have anything to do with newborns. But I was getting all cleaned up and taking my gray coat off and putting on these idiot scrubs, and I'm a lab guy. I don't deal with people. So Dr. Chesnoff drags me in, and I see this shoebox-sized 30-week-old premature infant with every tube known to man and monitoring device. I swore at that point I would never do that again. I have never been so angry and horrified in my life, and I beat it out of there. But when Ira asked me would I join the perinatal chemical dependence as their toxicologist, I said sure. By the way, those 3 drops of pee, well, we figured out it was benzoylecgonine, a cocaine metabolite that was in that urine. It was a pretty easy immunoassay, and there was enough benzoylecgonine in there that we could take literally 50 microliters, dilute it up, run GCMS, and confirm it quite nicely. So that got me an appointment that literally changed my life and changed my focus. In Time magazine, Ira Chesnoff was quoted as cocaine use is uniquely damaging for the fetus, far more damaging than any other narcotics. Ira was wrong. Cocaine is not good for fetuses, don't get me wrong. But the damage that was done prenatally, 99% of the damage was not the binging on cocaine. The damage was from the moms when they ran out of money and ran out of crack. They couldn't sleep. Just because the cocaine high had stopped, the cocaine levels in their brain was still exceedingly high. They were unable to sleep. And the cheapest sedative they could find was cheap wine. So a liter or two of cheap wine was what brought them down from their cocaine high. What we were seeing over the next several years, this epidemic of cocaine babies, what we were seeing were fetal alcohol syndrome or fetal alcohol spectrum disorder babies with cocaine layered atop of it. It was binge alcohol that was the culprit. We didn't have any means of identifying these alcohol-exposed babies. We had a compelling need for a long-term marker that could identify binge alcohol exposure. I'm not a crusader, but like I said, that trip to the neonatal intensive care unit had an impact on me. So a little bit of the history. Most of alcohol, conveniently, is oxidatively metabolized, and it forms carbon dioxide and water, and it goes away. The rule of thumb is, for every standard drink of alcohol, In the United States, it's considered 14 grams of alcohol. That's about 1.5 ounces of hard liquor, 12 ounces of beer, 5 ounces of wine. That's a standard alcoholic beverage. It takes typical adult 1 hour to oxidatively metabolize 99% of that dose of alcohol. What about the other 1%? Well, that's where we get into the non-oxidative metabolites. The stuff that doesn't get expelled through the lungs and forms something else, some other biomolecule, something that some guy like me or Joe or a whole group of other really bright group of scientists. The first one I'm going to talk about today is ethylglucuronide. Why ethylglucuronide? Well, because it was the first one that was really characterized. And it was positively identified, even though we knew that there were glucuronides, back in the early 1900s. They knew that you fed rabbits ethanol, they produced lots of glucuronides, more than would be expected. But it wasn't characterized until 1953. And R.T. Williams was the guy who did it. His laboratory did it. And for those of you that deal in drug metabolism, R.T. Williams is probably the godfather of drug metabolism studies. I remember in graduate school, his name was golden. One of my professors, Dr. Maynard, was our big drug metabolism guy. And we better know who R.T. Williams was. He was a biochemist in Great Britain. And he basically created the modern science of dosing animals, collecting urine, feces, and figuring out how to identify drug metabolites. Brilliant man. Well, he figured out the structure of ethylglucuronide and synthesized it. And then he received a standard from a Dr. Arntz from Corn Products here in Argo, Illinois. As I recall, wasn't Corn Products an early member of this organization? So there's a connection here. Corn Products knew about ethylglucuronide way back in the day, 1953. And ultimately, R.T. Williams formed a methyl ester, and he acetylated the 3 free hydroxyls. He had that compound all ready for gas chromatography. He just didn't have an instrument. We had to wait until 1995 before we got a good GC analysis published. And it came out of the University of Heidelberg in Germany, and it was a GCMS analysis. And this is the total ion chromatogram of ethylglucuronide from a human who had consumed a whole lot of alcohol. They formed the same triacetyl methyl ester, just like R.T. Williams, but their method of analysis was to take a millipede, take it to dryness. No extraction, just take it to dryness, bring it back up in some pyridine, derivatize it, shoot it on GCMS. Here are the conditions it was run on a Hewlett-Packard, not a natural, a Hewlett-Packard 5971, and they were using a big 5988 mass spectrometer. Everybody remember what a 5988 looked like? The big 4 model? Big guy, required water, whole lot of, I think it was, can't remember if it was an absolute 240, if it was a 208. I just remember whatever I had, it was the wrong voltage, and I had to either buck it up or buck it down. It cost me a fortune when we got one installed. They're over in Europe using Chrompack, methyl silicone column. Pretty simple temperature program. It's still not a very volatile compound. But it worked. And they had a limit of detection of 100 nanograms per milliliter. That's a limit of detection. Figure their limit of quantitation was probably about 500 nanograms per milliliter, which, believe it or not, is still about what we're running today, because at 500 we get around some of, well, I use Purell to wash my hands. You know, I got the ethanol from communion wine. You can think of any excuse known to man of how people get alcohol in their bodies. Turns out that urine ETG is a very sensitive test for recent alcohol use. When you go on a binge, you can have levels 1 million or more. So very small doses can produce measurable quantities of ethyl glucuronate, despite the fact that it's only about 0.1% of the total dose that gets converted. It's a pretty neat concept. We tried it. We did it. It's a slow, time-consuming process. After about 2 months of working with drying pee down, we decided that perhaps we would not go that route. So we put that one aside and decided we would do something different. We would either extract it and get a nice clean extract, and the lab just smelled really bad after a while. And for my people that are here that dry down samples, just imagine all those urine samples being taken to dryness just for fun. But we don't do that. So it was a little time consuming, but it was a step forward. We had a means if we chose to do it, but it was expensive, time consuming, but a huge step in the right direction. Now these are concurrent, and because I'm kind of a witness to some of this, a little bit of this is my own involvement. At about the same time frame in the early 1990s, the fatty acid ethyl esters were discovered to be biologically produced. Laposada and Lang first reported them in 1991. Mike Laposada is a pathologist. He's also a PhD biochemist. Lang was a lipid biochemist that he did his PhD work with. Laposada wound up being the head of labs at Massachusetts General Hospital and actually developed a methodology for looking at serum fatty acid ethyl esters. Well, I got a call from someone in 1992 asking me, could I do fatty acid ethyl esters in meconium? And I've been racking my brain trying to figure out how to do a biomarker for fetal alcohol exposure, and I grabbed that like you can't believe. It turned out extracting those doggone fatty acid ethyl esters out of the meconium mass, that tarry, gooey, biological silly putty, was a little more difficult than I thought it was going to be. The liquid extraction, really low recoveries, especially for the polyunsaturates. We were fortunate enough to get our first SBIR Phase 1 grant. For those of you who are not familiar with the SBIR program, it's a set-aside that the federal government has for small businesses to get a shot at the pool of grant monies that are available if you have an idea that you can show feasibility for, and then you can commercialize. So I grandly proposed with a co-investigator that we could come up with a way to extract fatty acid ethyl esters out of meconium, identify them by GCMS, and solve the problem of having a group of direct biomarkers to identify fetal alcohol exposure. great idea. The extractive process still wasn't good enough. The breakthrough came when we went back to Mike Laposada and just used his serum method. He was using an aminopropyl solid phased extraction column, and the problem with the polyunsaturates went away. We could extract them. We got close to 100% recoveries, all the way up through arachidonic acid ethyl ester, a 4 double bonded 20 carbon length fatty acid. And we were able to generate really nice chromatograms using a very highly polar SGE column, their BPX70. And basically we just used their fatty acid methyl ester temperature program. We used chemical ionization with just methane as our reagent gas. And it gave us a very, very good analytical methodology. We published our first data back in 2003. Christine Moore was our first author on it. Joe Jones is our second author. I just sat back and watched at that point. They reached a point where they took the instruments away from me, I'm sorry to say. I do all my chemistry on paper these days. And Karen Bouchai was a professor of pediatrics at the University of Utah. And we did a lot of the work with neonatal intensive care babies from the state of Utah. It was a very interesting study. Not too different. We had advanced to a 5973 system, running positive CI methane, as I mentioned, the BPX70 column, pretty simple temperature program, injecting at 100, 20 degrees per minute, up to 260. That column really doesn't tolerate too much beyond 260. We did selected ion monitoring, and our approach was to total the fatty acid ethyl esters and report the total, and anything above 500 nanograms per gram we reported as a positive. Probably was too low, but at the time there was no data. We didn't know whether 50 was the right number, 500, 5,000, 50,000. So we pulled a number, and it seemed to be appropriate. The Hospital for Sick Children in Toronto came up with about the same number, just in international units. I won't throw those out because they confuse me. But we had something that seemed to work. And the fatty acid ethyl ester analysis was rapidly then extended into hair testing. If it worked in meconium, my goodness, it should work on adults in their hair. And it was especially favored in European labs. They like to use a SPEMI injector. I have no experience with the SPEMI, so I can't really tell you too much other than what I see in the literature, but that seemed to be a pretty good approach. But then some issues got cropping up. There were denials. I don't use, you're wrong. You know, we hear that all the time in the forensic world. Except some of these were probably real excuses, because it turns out that there are fatty acid ethyl esters in some hair products, some cosmetic products. And then if you put ethanol on human hair, there are fatty acid synthase enzyme in the hair. You make fatty acid ethyl esters in the hair itself, in situ. And what was worse, in our meconium samples, we have, in this country, we went from using washcloths and water to using ethanol wipes, and the most convenient thing once they went to disposable diapers was you use the ethanol wipe on the baby's bottom, you throw the wipe in with the diaper because you're going to throw that away. Oh no, yeah, we're collecting meconium now. Meconium has the fatty acid synthase enzymes in it as well. You put meconium, put it in contact with ethanol, and you synthesize fatty acid ethyl esters. A classic pre-analytic variable we had no control over, but we would get some samples with enormous levels, and it didn't prove the baby was exposed or the hair was a true positive. That's not a forensic test, unfortunately. If you can't differentiate the false positives from the real positives, at best it's a very expensive initial screening test that needs to be confirmed by another method. And you don't want a $200 screening test. This is part of the learning process. And I bring this set of compounds in because we were gung-ho about it. It looked so good at first. But it took us several years to realize, oops. That's how we learn. And while all this is going on, a whole nother group of compounds, phosphatidylethanol. It's not one compound, it's a group of abnormal phospholipids. First discovered in 1983, at least first reported. And almost simultaneously in Europe by Ehling's group and at the University of Wisconsin at the McArdle Cancer Institute. Two entirely different lines of research. But both groups came up with the same thing, that when you have any mammalian cells in alcohol and phosphatidylcholine, which is present in virtually all mammalian cells, you get this abnormal group of phospholipids, which are phosphatidylethanol. And it's a whole array of them because there are two sites where you esterify long-chain fatty acids, and then the phosphoethanol group. That's the common element. The neat thing about, since it's in almost every cell in the body, well, one of those groups of cells that this reaction takes place in is the red cell. It's kind of hard to go in and do biopsies and get brain tissue to do with the analysis, but it's not real hard to get red cells. That's what we do venipuncture for. And this is a wonderful diagram of the red cell membrane. But in the red cells, phosphatidylethanol gets formed and it just incorporates into the red cell membrane, and it sits there and doesn't do anything because humans, we lack an enzyme to break it down. So it just sits there until it spontaneously hydrolyzes. And in humans, it has a half-life of about 4.5 days. And that's the key part about it. Because it has a very reproducible time to hydrolysis, we have a pretty good idea how long it's going to last. And we also know the kinetics of formation. If you have one drink a day, you form very, very little. You have 2 drinks at a sitting, again, very little. But when you start having a 6-drink binge, all of a sudden you get a disproportionate increase in the amount of phosphatidylethanol that gets formed. Won't go into the kinetics of it, but we have a real neat little graph that shows how it works. A paper came out in 2010. From Berlin. Went through the pharmacokinetics, and it's very, very well done. And it describes why this compound spikes when you binge drink, not when you drink at modest levels. Makes it the ideal marker for what we were looking for. The Swedes were the first ones that really got interested in looking at it in blood. And what they did was they looked at it using HPLC with an evaporative light scattering detector. Pretty good technology. for the 1980s, but relatively insensitive. So what they were able to identify were really heavy drinkers, like people that drank 10 drinks a day, every day. Those were the kind of cases that they were routinely able to identify. Okay, that's a pretty good test, but in that kind of individual, maybe you don't need a diagnostic or forensic test necessarily. You just count the bottles. And the other drawbacks were it was a liquid extraction. Took a little time. But the really beautiful thing about being an observer and watching how this evolved, because it was something we really wanted to do, and actually we were doing. And we started off using entry-level instruments and said, there's a peak there, but not too much better than the light scattering detector. But those detectors kept getting better and better. The mass spectrometers, the tandem mass spectrometers just kept getting better and better. And before you knew it, sensitivity kept increasing. And we're at the point now where we don't need even to do venipuncture. We can do it on a dried blood spot from a finger stick. That's how much the sensitivity of the instrumentation has changed. And if you don't think that's not a game changer in the world of alcohol biomarkers, believe me, from 2005 until now, the world has changed. Now, phosphatidylethanol gives us the ability from a finger stick or a little bit of umbilical cord blood just on the dried blood spots. We can do the analysis. Let's see. Whoops. Somehow, some of the text got out, so that's okay. That's what the dried blood spot card looks like. It's very small. It goes into something kind of like an old match type box. That was Joe's idea. Because these are forensic tests, they need to be allowed to air dry. Well, if you put it into the box and seal the ends, it's sealed. It's a forensic seal, but it has the ability to air dry. You don't have to have somebody sit and stare at it for 3 hours while it dries. Just have them sign it, off they go. And we can extract 3 punches out of those little circles. And that's sufficient to do the analysis. What makes it even more interesting is the LC part, the front end, the micro LC. Lowers the time to run these. We've gone from run times in the 7 to 10 minute. Let's get a chromatogram up here. There we go. I know this is a little small, but if your eyeballs are good enough to see the numbers, the time in minutes, these are eluting in the between 7 and 8/10 of a minute. So we're getting injections sometime less than every 3 minutes after it comes back to equilibration. Things are moving through the laboratory with just, a few tens of microliters of blood, 3 minutes. We don't have to extract other than a quick methanolic extraction off of a dried blood spot. This has just been a huge game changer. Like I said, this worked on adults. We started developing this really for babies. We were thinking about heel sticks. We did a study about 6 years ago with a collaborator in Uruguay, in Montevideo. And we got paired samples from we got dried blood spots from the heel sticks, we had meconium for fatty acid ethyl esters, and we did have umbilical cord samples. And we looked at phosphatidylethanol in the umbilical cord. And when we plotted everything out, nothing made sense. Because the dried blood spot data was so much, we had so many more positives from the dried blood spots compared to the other matrices. So we made the assumption now something went wrong. They screwed up, they contaminated the samples, something was wrong. So we set it aside. We thought, there's a problem. So we'll get back to that, but we couldn't figure it all out. About 3 years ago, a group at the University of New Mexico effectively repeated what we had done on a little smaller scale, and they got exactly the same results. The dried blood spots were about twice as sensitive an evidentiary tool as fatty acid ethyl esters and meconium. Or, Joe, do you remember, did we do anything else on those?
PETH in the cord.
We did do the PETH in the cord. So basically, duplicating the study we had done down in Montevideo, it was almost, you could almost superimpose the data on top of our original data. And we just start banging our heads against the wall and go, oh my God, what a bunch of fools. We can't tell you why this fetal blood spot is so much better than any other tissue we found. All we can tell you, it works. We don't know why, but it works. So now we've got something that we're really thrilled about. We have another study. We're trying to go back to Montevideo and follow the kids longitudinally to try and see if there's a way can we, from what the levels are at the time of birth and perhaps what their epigenetics looks like, how will these children develop? Which ones will show signs of fetal alcohol spectrum disorder as they get to 2 years, 3 years, 5 years, maybe even extended on to 10 years? To get a truly diagnostic picture of what's going on. And that study group meets November 6th, and we will find out whether we're going to Montevideo for the next 5 years. Now, the other big thing that all this sensitivity brought us, it let us experiment with other matrices. I told you about trying to do FAEEs in hair. Well, ETG also was done in hair. And it also had some of the issues. You bleach your hair. Peroxide, unfortunately, hydrolyzes ETG. But what about fingernails? It's also a keratin matrix. Would ETG incorporate into fingernails? Would that give us a matrix that doesn't get damaged by cosmetic treatments? And since it grows in 2 dimensions rather than just a single dimension, because it grows both in length and in thickness as it grows along the nail bed, it perhaps would give us an interesting data set. So how might that work? Well, we had the sensitivity, and here's a nice cartoon of the nail. And if you look down on the lower panel, all along that nail bed, wherever it's in contact with the nail bed, the nail is growing in thickness, as well as growing in length from the terminal matrix back at the most proximal end of the nail. So your nail looks like a pyramid. It gets thicker as you go along, which makes it kind of neat because more recent use is still there. You clip the nail at the end and you're not waiting 6 months for the growth from the very beginning. That includes everything up until it comes off the nail bed. So we proposed an SBIR grant, and NIAAA funded it. It allowed us to do 606 paired samples from college-age students. And I'm just going to summarize. The gist of it was fingernail ETG on average was 2.5 times higher than the hair concentrations. And the ETG correlated really nicely between the male's hair and fingernails. It didn't correlate well between the female's fingernails and hair. There was a gender bias. And we think that the gender bias is totally due to cosmetic use on the hair. Bleaching, dyeing, perming, straightening. And there was really no difference in compliance. We got no statistically significant difference between the number of hair samples and nail samples. So it wasn't like, a lot of people chew the nails, we couldn't get samples. No. It was about 98 point something percent on both hair and nails. So compliance wasn't an issue. Our conclusion was nails is a better sample. Get higher levels, doesn't get as contaminated. And this is just a picture of what the samples look like and the grant number from NIAAA. Well, I've had 45 minutes to tell you about this little journey we've taken. And we've come an incredibly long way. From when we first discovered what the hell ETG was, to having validated, truly validated forensic tests that let us look at 3 entirely separate time windows. And this is kind of the take-home message of the day, is that now in the analytical lab, we can look at a 3-day look back using a urine sample and looking for ETG and its cousin ethyl sulfate. I didn't talk about that today. It has a little different history, but its companion has the same kinetics as ethyl glucuronide, and we do them together. Phosphatidylethanol is up to about a 3-week look back. So now we're going from about 3 days max to a 3-week look back. Different window. It seems like the therapists think that's the sweet spot, that 3-week, because that's a big binge. One big binge gets you up there. And then the fingernails and hair give you about a 3-month look back. That's multiple binges. That's not one binger. That's looking at a pattern of behavior. The departments of transportation, when they're trying to rehab multiply convicted drunk drivers, they really like the fingernails, because that gives them an idea of, does behavior really change over the long haul? And then they want to put 2 tests 3 months apart to get down to negativity before you get your driver's license back. A lot of things that are going on in this world. That's my story. And I will open up the questions, and I want to thank you for listening and not throwing things at me. Thank you very much. Oh, one last thing. None of this happens without the instrument manufacturers constantly improving their instruments. I can't say enough about the R&D from everybody who's in the mass spec business right now and the chromatography business. You guys don't bring out these innovations, we don't develop these new procedures, because it was totally dependent on high sensitivity triple quads and improved chromatography. The academic researchers, like I said, I steal ideas. I don't come up with them myself. I work by analogy and other people's research, and then I figure out how to weasel them into our work. And then there are a few risk takers. I know my wife goes nuts when we try these things, but some of them work. And she's smiling. Many of them do not. But it has been a wonderful ride, and it's a lot of fun.